Hi everyone, my name is Peter. Welcome to this section. Today we are going to discuss organic chemistry 1, and today's topic is going to be reactions of alkenes. So under this we shall look at additional reactions, but before that we have to look at these three major terms that we are going to encounter through organic chemistry, not only in this chapter but all over organic chemistry. So these are one of the major concepts you need to know as we go on in organic chemistry. So we shall begin with the carbocation stability, then hyperconjugation, and then lastly we shall look at what we call the regioselectivity. So to begin with the carbocation stability, so in organic chemistry we see out of molecules, especially if an alkene reacts and leads to production of a carbocation. So we shall look at its stability, and the stability has an order whereby tertiary carbocations are more stable than secondary carbocations, and secondary are more stable than the primary. So an example of a tertiary carbocation is when you have three carbons bonded to one carbon. So this carbon is less is less by one. So remember, carbon has to be bonded to 4. This one is bonded to 3. So it forms what we call a carbocation. And the stability of carbocations is that tertiary is greater than secondary and greater than primary in that order. So therefore, a good example of a secondary carbocation is when this carbon is bonded to only 2 something like this, only 2 carbons, and for primary it's basically something like this. So now under hyperconjugation explains why does tertiary carbocations are more stable than secondary, and also and primary carbocations are the weakest. So now we are going to use a hyperconjugation theorem to explain why this is more stable compared to secondary and primary. So with this I will illustrate this using the molecular models. So here I have my molecular models. So this first one is a molecular model for, let me begin with the tertiary because it's the most stable one. So this is a good example of a tertiary whereby this carbon is bonded to 3 other carbons and it has this bond. So usually this plus on the carbon means that we have an empty p orbital. So remember that carbon has an electronic configuration of 1s2, 2s2, and 2p2, whereby if I'm to draw, this is the 1s, 2s, 2p. So we have 2 electrons here and 2 electrons here, 1 electron and 1 electron. So when this carbon here has an empty p orbital, meaning that this electron is not there or is taken, so this p orbital is almost empty. So when the p orbital is almost empty, what is going to happen is that we are going to have what we call hyperconjugation, whereby the nearby pi bonds, the carbon to hydrogen, sigma bonds, contribute electrons to kind of neutralize the positive charge on this carbon. So what really happened is that you see these carbon to hydrogen bonds we have here all over. So these carbon to hydrogen bonds are going to overlap with the p orbital this empty p orbital here. So what really is going to happen here is that let me rub off this for a moment. So these are this is my carbocation, and these are the hydrogens that I've been showing you. So what's going to happen is that this carbon here has an empty p orbital. If I may represent the empty p orbital with something like this. So now these electrons here, these sigma bonds, will contribute electrons towards this p orbital. So what's going to happen is that this will contribute, and this will contribute, and this will contribute, and this, and all these three will contribute to the stability of this carbon. And in the result, as a result, we are going to form a structure whereby the positive charge will not only be on this carbon, but the positive charge will distribute all over these molecules. So these partially positive charges are going to distribute all over the molecule. So therefore, this carbon here is not only going to feel the loss, but all these are there for it so that it feels comfort, if I may say. So therefore, that's why the tertiary carbocations are more stable than the secondary and primary, because it has 9 carbon to hydrogen bonds, and these bonds contribute to its empty p orbital, thereby distributing the positive charge from this carbon to all these carbon to hydrogen bonds, and leading to the stability of the molecule. So to illustrate this with a secondary carbocation, so this is my secondary carbocation. It's still the same concept, except that this one has 1, 2, 3, 4, 5. This one has 6 carbon to hydrogen sigma bonds, and these sigma bonds are going to contribute to this carbocation so that they lessen the burden. So they're going to share the burden. They're going to share the positive charge. So all these will come partially positive, except this one, but this rest will be partially positive, hence stabilizing this carbocation. And then lastly but not least, we have the ethoxy carbocation. So this is a kind of secondary, but it has one methyl group. So therefore, these carbon to hydrogen 3 bonds will contribute to this, and therefore leading to its stability. And then lastly, we have the methyl group, which does not have any carbon bonded to it. So therefore, this is the least stable carbocation. So therefore, under the hyperconjugation, when we draw the curve for energy versus this is the progress of the reaction. So we shall see that as energy so if this is for the tertiary carbocation formed at this point, if this is my tertiary carbocation here, so this tertiary carbocation has a lower activation energy from this point to that. But if you're to draw one for secondary or one for tertiary, we shall have that these will stretch a bit higher compared to what? To the one of tertiary, meaning that you need more activation energy to form that carbocation. So meaning that the tertiary carbocation is more stable, has lower energy compared to the secondary and primary. So therefore, with that, let me jump to go to what we call the regioselectivity. So under regioselectivity, this we shall see in most of the mechanism of actions that we shall do under here. So regioselectivity is all about which major compound is being formed which compound is preferred as a product over the other. So this is basically determined by the stability of the carbocation. So as we begin this chapter, when we see the mechanisms of action, I will refer more with radioselectivity and see how it's applied under reactions of alkenes. So now, to jump into the mechanism of action of additional reactions. So the first reaction of alkenes can be reaction with a hydrogen halide. So an example of hydrogen halide, we have HCl, HBr, and HI. So these are the hydrogen halides that react with an alkene. So for the general reaction, if this is my alkene and I react it with a hydrogen halide, for example, HCl, so what we're going to have is that this pi bond has a number of electrons. So these electrons will attract this hydrogen. Remember, this bond is polar, so therefore chlorine is more electronegative than hydrogen, so we shall have partial charges. So these electrons will come and bond with the hydrogen, and this bond breaks off in favor of the chlorine atom. Then we shall form something like this. So this will be our product. Then this chlorine atom will come and bond with the carbon. Then we form our alkyl halide as our product. So this is the major reaction of all alkenes. So in my next chapter, we are going to do more of the mechanism of action and more examples. So thank you very much. Tune in next time as we discuss further the halogenation of alkenes. Bye for now.